All right, so this is chapter 11, talking about liquid, solids, and intermolecular forces. I decided not to finish this at the end of 170. Thought it'd be a nice review to start this semester. So let's talk about solids. Solids are dense, they're not compressible, they're rigid, and they have no freedom of motion. The particles are still in motion, but they're just kind of vibrating. So, who is a foot shaker? All right, I tend to be too. So think about that. That's kind of like what a solid does. You are not actually moving anywhere, but you're still vibrating a little bit. Okay, that's how solid particles are. Liquids. Liquids tend to be slightly less dense than solids. They're also not particularly compressible, but liquids flow. We'll talk about that next chapter. They flow and they're going to take the shape of the container. A liquid itself has no definite shape. Their particles are going to move. They're going to kind of slide past each other. They got a little bit more freedom of motion. Gases, not dense at all. You can compress gases. We can say they're compressible. How about that? Compressible. I like that better. They are going to expand as much as you will let them, depending on the container you have. And gases have complete freedom of motion. They're compressible. Who popped the top off of their flask when we were doing gas laws? Anybody? I did. When you're adding the gas on the part 4, yeah, I popped the top on mine. All right, now I'm going to try to enunciate this correctly because this is not meant to be confusing, but these words sound and look similar. So try not to confuse them. We're talking about intermolecular forces. But before we talk about that, we're going to talk about intramolecular forces. They are not the same thing. All right, so intramolecular forces mean within the molecule. And primarily when we're talking about an intramolecular force, we're going to be talking about bonds. Bonds and charges. So ionic bonds, covalent bonds, metallic bonds. Larger charges. They're going to cover very short distances. And intramolecular forces within a molecule are always going to be stronger than intermolecular forces. So this is the stuff we talked about at the end of 170, and we're talking about bond theory and such. Now, what we're actually talking about, intermolecular forces. These are interactions that are between our actual different molecules. So how one water molecule interacts with another water molecule. Now, intermolecular forces tend to have less charge. They're across a greater distance because they're not within a molecule. And so they're going to be weaker than an intramolecular force. There are several kinds. The first one is called a dispersion force. We can say dispersion force, or you can say dispersion. Some textbooks you see may refer to this as a London dispersion force. That's the guy that discovered them, named them after himself. Can't blame him. He probably got a Nobel Prize. So I learned them as London dispersion forces. So just in case you hear me say that, a London force, this is what I mean. So, but this textbook does not refer to that, but in case I slip. All right, it is a force that occurs between temporary dipoles. Who can tell me what a dipole is? Yes, Catherine.
Is that when like one's negative, one side is negative, and the other side?
Yes, so within a molecule, you have a partial negative charge and a partial positive charge across a bond. And it can happen even in a nonpolar molecule. All molecules can have temporary dipoles, which means all molecules can have dispersion forces. So if you have one of those questions where it says select all the forces, dispersion forces every time. It's always correct for an intermolecular force. All right. It increases with an increased size of a molecule. Because when you have a larger molecule or a larger atom, so as we go further down the periodic table, these are going to hold their electrons more loosely. They're further from the nucleus. So that means they can be polarized more easily. So they can be pulled closer to one atom than another within a molecule. So it's easier to create this temporary or permanent, potentially, separation of charge. And then it's going to decrease when you have a molecule that has branching. This is important when you get to organic. So molecules that are, instead of being straight like a train, they can kind of branch out. Because branching makes a molecule very round, and a round sphere has less surface area than a train track type molecule. So if you're dealing with a question that says which is going to be more, have stronger dispersion forces, they're still very weak, but big molecules that are straight are going to have the strongest ones. Every molecule has dispersion forces, or is capable of it, even non-polar ones. All right, let's talk about dipole-dipole interactions. This is a force that occurs between the partial charges that are on adjacent polar molecules. All right, what's a polar molecule? Who can give me an example? Water. Water is an excellent polar molecule. Let's draw it. Water. All right. Oxygen is very electronegative. Hydrogen is not very electronegative. So even though they're sharing these two electrons, I'll draw it where this hydrogen is positive. The arrows are getting pulled closer to the oxygen. You can also draw this, if you prefer the delta method, as a delta positive, partial negative. I'm okay with either one of those. But, so this is not going to change. Oxygen is always going to pull the electrons more strongly than hydrogen is. So here, dipole-dipole, you can have this hydrogen interacting with this oxygen, because the partial positive and the partial negative are going to attract. It also serves as an example of hydrogen bonding. Okay, we call it hydrogen bonding. Hydrogen bonding is not a bond. We still call it that. I'm sorry, it wasn't my idea. But think about what we just talked about here with water. It is the attraction of hydrogen. So the hydrogen in a molecule that is bound to a highly electronegative atom, and these are going to be the ones that you're going to notice: fluorine, oxygen, and nitrogen. These are the highly electronegative atoms that are going to be associated with hydrogen bonding. So, do you see how this hydrogen is connected to this electronegative oxygen? Yes. Good. So, same thing that happens. Dipole-dipoles don't have to be hydrogen. That's kind of the caveat there. So this is both a dipole and a hydrogen bonding. But, so it's going to be the hydrogen on one molecule, because it's stuck to a highly electronegative one, to another fluorine, oxygen, or nitrogen on another molecule. So this hydrogen on this water molecule to this oxygen. It's not talking about the attraction within that molecule. All right. Highly electronegative atom, and hydrogen bonds, because you're dealing with strong electronegativities, it's a highly polar bond, is going to be stronger than your typical dipole-dipole. Let me see if I can think of an example. Let's find a polar molecule. Polar molecule, we can do, if we do like HCl, chlorine is more electronegative, so here you're going to have attractions there. Particularly when you get to organic, if that is your particular persuasion, you'll be dealing with a lot of hydrogen bonding. Or if you want to go into biochem, tons of hydrogen bonding. We talk about DNA synthesis. I don't get to teach that, but it's one of my favorite things to talk about. All right, so dispersion forces number 1, dipoles number 2, hydrogen bonding number 3, ion dipole forces. This is what occurs between an ion and a polar compound. Particularly when you're talking about, I didn't put it on here. All right, particularly when you're talking about an aqueous solution. Of ionic compounds. So when you have like NaCl that's dissolved in water, so you have Na plus Cl minus, the Na would be attracted to the Cl on an undissolved molecule. You're going to have an attraction there because this is an ion, this is still a molecule. Not meant to be difficult or confusing. Don't make it harder than it is. Yes?
Is that a dot between the chlorine?
Yeah, right here?
No, on the bottom.
Down here. Yeah, it's like a little trail of dots. Sort of like, because this is what's attracted, this chlorine to this sodium.
So is that showing
That's
the
the attraction.
Is it showing the bond?
It's not a bond. It's just a force. It's showing the attraction. That's why I have it as a broken line. If it were a bond, it would be a complete line. Okay?
Gotcha.
And that's why, like, with hydrogen bonding, it's not actually bonding because you're not drawing a full line. They're not sharing electrons. It's not an ionic bond. Either. It's a good question. Anybody else? Questions?
So like molecules change in the environment. There's the dispersion first for the intermolecular force.
Mm-hmm.
Like in space, would that be decreasing? Because like you have, like you drop liquid and it turns into like a round of ball.
Oh, because of gravity?
Yeah.
Or lack of gravity?
So
Yes.
is that decreasing or?
You would have a decreased, you would have a decreased dispersion force because of the shape. Yeah, because you have a decrease in surface area. Yes. Not something I tend to contemplate, but that's a good intellectual exercise. All right, let's turn the page. All right. Why do we care about this? Once it goes in focus. Okay. Intermolecular forces in action. All right. Let's talk about surface tension. Surface tension is defined as the tendency of a liquid to want to minimize its surface area. Surface tension is why you can see those like water bugs that walk across the water, kind of glide across the water. I don't remember what they're called, but how that happens. But what ends up happening is surface tension of a liquid. It's going to create a skin of sorts that's going to resist penetration. And that's about as complex as I'm going to make it. It's there, it exists. But so in the surface of a liquid, the intermolecular forces, like of water, they're going to try to stick together so they don't spread out as much. They would rather stick together because they have hydrogen bonding. Now, another property of liquids is viscosity. What common term do we tend to use for viscosity? Thickness, yes. So thick liquids are viscous. They resist flow. What pours easier, honey or water? Water. There we go. All right. So it's going to resist flow if the viscosity is going to be greater. So it's going to manifest as appearing thicker when you have stronger intermolecular forces, because the molecules want to stick to each other rather than slide past each other. They're like, oh, hey, hey, hey. It's like going down a line and giving everybody a high five. And how do you get honey to pour easier? You warm it up. You put it in the microwave. Somebody, at least other than me, drinks tea. All right. So decreases, if you want to decrease the viscosity of something, you increase the temperature. You heat it up. It's going to decreases. Subject-verb agreement. All right. Because when you heat something up, things are going to move faster. They're going to have less opportunity to stick to each other because they're moving faster. Does that make sense? Anybody missing blanks? Don't suffer in silence. Okay. Capillary action. Who's used a capillary tube before? Who's had a capillary tube used on you? If you've ever given blood, it's that tiny thing that's just a little bit wider than like the lead of a pencil. Pulls the blood off of your finger up into the tube. All right, so capillary action refers to the ability of a liquid to flow against gravity up a narrow tube. Because normally water goes down pipes, right? Yes, not up. Okay. Now, you have how capillary action works. Depends on two things. You have adhesive forces that occur between the liquid and the surface of the tube. If it's going to move up, your adhesive forces, so it wants to stick to the tube more than cohesive forces, which is between the molecules in the liquid itself. So it wants to stick to the tube, it wants to stick to the glass more than it wants to stick to itself.
Is that how siphoning works?
Siphoning generally has pressure involved. So the best example of capillary action I've got is the blood in the little capillary tube. We used capillary tubes in lab when we did yes, yeah, the ones that break real easy. Chromatography, where we put the stuff on the filters and put it in the solvent and dissolved it up, because we picked up the liquid in the capillary tube, put our finger on it, and dropped it. Yes. So a liquid that has capillary action prefers to stick to the surface, usually glass. We'll write that down. Usually glass, more than it prefers to stick to itself. You can also see adhesive and cohesive forces in a meniscus when you're measuring liquid in a graduated cylinder. So water prefers to stick to the glass more than it prefers to stick to itself. That's why you get the dip that is, concave down. Whereas if you have mercury, mercury loves itself. So if you put mercury in a graduated cylinder, it's going to concave up because it would rather stick to itself than the tube. So it is possible to have a meniscus that is concave. All right, how they are in action. More things that we care about. Vaporization and vapor pressure. We're going to be talking about this next chapter too, I think. All right, so vaporization, what is it? Yes, transition of liquid to a gas. So if you're going to go from a liquid to a gas, this is lower energy to higher energy. Whatever intermolecular attractions exist, we have to overcome them, so we have to break them. Since they're not actually bonds, broken may not be the best word, but so we can also say overcome. So, vaporization increases by a temperature increase, right? Water's going to evaporate a lot faster when you boil it than when you leave it sitting in the room. It's also going to increase when you increase the surface area. What's going to evaporate faster? Water that I spill over the desk or water that I have in a glass? Where it's spilled over the desk. Again, don't make this complicated. Don't overthink it. All right? And if you have decreased or weaker intermolecular forces. So, think about water versus rubbing alcohol. Rubbing alcohol has fewer intermolecular forces because there's no hydrogen bonding. So it's going to evaporate a lot faster than if you put water on your skin or just on a surface. So non-polar molecules tend to have very low boiling points. They would rather be gases because they have nothing to hold them together as a liquid or a solid. Maybe not nothing, but they have less holding them together. All right, so non-volatile compounds are what we refer to as compounds that do not vaporize. But volatile compounds do vaporize. Now, you can tend to make something that is non-volatile volatile if you heat it enough. But, you know, steel tends to be non-volatile, right? Do we ever see gaseous steel? Not normally. That would be bad. All right. So that's the example. All right. Oh, don't tell me that I'm wrong. That's just rude. I'm just kidding. Always point out when I make an error. All right. So vaporization is, here's your choice, endothermic or exothermic? Endothermic. Yes, it is endothermic. Because energy input, we have to put energy into the system, is required to break the intermolecular forces. The opposite of vaporization is condensation. So vaporization is liquid to gas, condensation is gas to liquid. There's a U there. Okay. All right, so condensation is not endothermic. It is going to be exothermic because energy is going to be released from the system when our intermolecular forces that are not really bonds, but when those forces begin to occur, because that's going to put the system in a state of lower energy, which is where it wants to be. So these molecules connect with each other, they're happy, so they spit off some heat. Maybe a little, maybe a lot. So condensation is exothermic. All right, if you think about it, this is how sweat works. Sweat uses the heat of your skin to fuel its endothermic process. That's why when you put a fan on yourself, you get cooler, because you're harnessing the endothermic properties. The body's pretty smart. All right, now let's talk about the heat of vaporization. Let's start by this, it's important. We are going to abbreviate it as delta H vape. It's kind of a hot button term right now, isn't it? Yeah. We say vap, but that sounds weird because you don't vaporate, you evaporate. I don't know. Whatever you call it. Anyway, pronounce it how you want to. I won't get mad at you. All right, it is the amount of heat energy that is required to vaporize 1 mole of the liquid. So what kind of units are we going to have? Energy per mole, usually kilojoules. Why do we care about this? Units are our friends. That's right, units are our friends. Man, it only took me 30 minutes to say that. It's probably a record. Okay, so now, heat of vaporization is, so from liquid to gas, so for water, is positive 40.7 kilojoules per mole when you're at 100 degrees. So that's boiling point of water. It does change with temperature. We're not going to get into that too much as far as how it changes. The problem will tell you this is the heat at this temperature. Roll with it. All right. Now, let me tell you. So if you get a heat of vaporization and the question asks you how much energy is released when something condenses, it would be, so the opposite, because heat is released, right? So vaporization is an endothermic process, so condensation is negative delta H vaporization. Condensation equals. So you can go either direction. The value is the same. The sign will change. Just think, what is the system? What is the surroundings? Where is the heat moving? Is it going into the system or out of the system? Into the system is positive. Out of the system is negative. It's the reason I don't like thermodynamics. But anyway, nevertheless, I can do it. Okay, so let's try this. You've probably done this before. How much water can be vaporized at its boiling point with 100 kilojoules of heat? All right. So I'm going to say we're starting with 155 kilojoules. If you don't like my factor label method, that's fine. Make sure I can follow your math. Show your work. Show your work. All right. So now we got to get rid of kilojoules. So we know that this is our heat of vaporization. So we know we're trying to vaporize, so we're going to keep it positive. Also because we can't have negative mass. Kilojoules per mole. We're dealing with water. Units are our friends. You can say 1 if you want. Keep track of it. All right. And now, are we finished? No. What's the product? What's the question asking us for? Grams. All right. Use your periodic table if you need it. 1 mole of water is, we're going to say 18. We'll go with 0.02. Again, if you put 18, it's going to be close enough. Don't worry. All right, we do need our calculators. I didn't bring mine. Thank you. 68.6 grams of water. There we go. And we put a box around it. Feeling better about this already, right? Sure. Heat calculations. All right. Again, this is not meant to be difficult. Next one. Amount of heat in kilojoules. Here we're vaporizing 2.58 kilograms of water at its boiling point, so we can use our standard conversion. Don't memorize this heat of vaporization. I will give it to you.
Sounds like a challenge.
Yeah. Well, you can memorize it if you want to, but that's not what I'm going to tell you to waste your energy on. Okay, so let's start with what we know. 2.58 kilograms of water. Can we do anything with that value? Not yet. We got to convert to what? Grams. Let's convert to grams. So 1 kilogram, 1,000 grams. That it will not give you. That you definitely need to know. Where do we go next? We go to moles, that's right. So 18.02. I just stole that from the previous page. Grams is 1 mole of water. Now we can go from moles to heat, right? All right. So we want 40.7 kilojoules per mole. Is it positive or negative? Positive, because we are vaporizing, so vaporization is endothermic, so we should have positive heat.
5,830.
Yes, 5,830 kilojoules, or 5.83 times 10 to the third kilojoules. Both are acceptable. Questions? Let's make it complicated. It's a final temperature calculation. Oh, we don't like these, do we? No, that's okay. Yes. 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 Go back up. That's a 3. You can't read. If you don't like scientific notation, don't use it. You can put the zeros. It's fine with me. I don't care. If you're in lab, we might talk about it, but that's more of a significant figures thing. In lecture, after the first test in 170, I don't care about significant figures. All right, next question. You have 0.48 grams of water, and it's going to condense on the surface of a 55 gram block of aluminum. The aluminum is also 25 degrees. If we don't lose any heat to the universe, which is not possible, but theoretically, what's our final temperature of the metal block? Here we have heat of vaporization and heat of aluminum. Okay. So, we can use MCAT, but, and we will, I worked this problem in 2 steps. You can work it in 1 if you want to. But the first thing that I did is I said, let's find the heat released. So I decided to start, and again, you can start in a different way depending on how your brain works. But I started with my water and said 18.02 grams is 1 mole. And look here, at 25 degrees, it's different than it was at 100. Notice it takes more energy to vaporize it. So, all right, so we know it's going to take 44.0 kilojoules per mole. But so now we're condensing. So what's our sign? Negative. It's negative. Because when it condenses, it's releasing heat. This saves you from having to remember that negative Q water and positive Q metal. That's why I did it this way. If you wanted to do it and set them equal to each other in 1 step, you can. Who's got an answer for me? We know it's going to be negative. Negative what?
1.17.
Yeah. 1.173 kilojoules. Something like that. If it's close, roll with it. You get some grace on these. Now, that's why I'm your favorite. All right, so now we know that this heat that is lost by the water is going to be gained by the metal. So we know that negative Q water equals Q metal. That's from chapter 6, our thermodynamics there. Now, the specific heat of our metal is in joules. Right now we're in kilojoules. It will save you some time and effort and possible headache to go ahead and say that this is negative 1173 joules. You can do it in the second step, that's fine. So heat lost by water is gained by the metal. So how much heat is gained by the metal? Yeah, 1173. Don't make it complicated. Because here you have negative of a negative. All right. Heat equals MCAT, yes. MC delta T.
So is it
55 grams.
times the 0.93?
Specific heat, 0.903 joules per gram degree Celsius. Grams go away. We don't know what our final temperature is. We do know our initial temperature is 25 degrees. Now, we can work from here. I'll have my calculator with me. All right, what is 55 times 0.903? Somebody tell me. 50? Okay, so that'd be 50 joules per degree Celsius times T final minus 25 degrees Celsius. I keep all my units there because I make sure they cancel. What do we do next? We got to distribute. Yes, that's where everybody messes up. Maybe not ever. If you don't mess up, you don't mess up. That's great. But if you mess up, this is the most likely spot. It's going to be there, or it's going to be forgetting. It's going to be leaving this in kilojoules. Okay, so 1173 joules, 50 joules per degree Celsius times T final. Minus, because we're not distributing a negative, 50 times 25 is 1250?
Yeah.
Okay. 1250. Now here, degrees Celsius are going to cancel, so we're left with joules. Now what do we do?
Yeah, add 1250.
Yeah, we got to move it all to one side. Yeah. All right. So how many joules do we have? 1250. 3, 2, 1, 4, 2, 4, 2, 3. All right, I can add. Good. Is 50 joules per degree Celsius. Divide it out, so let's divide by 50.
48.46.
Yeah, so we can say 48.4656, something like that, degrees Celsius.
Hey, Dr. C.
Yeah.
I did round on the 50.
Yeah. So did you get a higher number?
Actually, I got lower. I got 1241 instead of 1280.
Okay, so what'd you get for your final temperature?
I got that right.
Oh. That is acceptable. Remember, I'll follow your rounding. Final temperature calculations are about as hard as it gets in this. So if you feel good doing this, right on.
Yeah, this chapter.
In this chapter. No, it's going to get way worse.
Oh,
Oh, in this chapter?
No, not in this chapter. Yes.
How come up there, whenever you multiply the TF and the 25 degrees Celsius, you multiply it by 50 instead of just going ahead and dividing the 50 out?
You can.
All right.
You can if you want to.
Okay.
Did you get the same answer?
Yeah.
Yeah. That's fine.
are we skipping chapter 12?
We are skipping chapter 12, yes. I made that executive decision.
Hey, I'm with you.
So I would rather have more time to cover things that I think are a little bit more important. If you disagree, put it on my evaluation.
Chapter 12, that's third.
Chapter 12 definitely just went out. All right, so let's talk about vapor pressure. Vapor pressure. All right, this is a term you've seen before in Gen Chem 1. We're going to see it all the time this semester. Learn it, love it. Dynamic equilibrium. Dynamic study module is also appropriate. But dynamic equilibrium, it occurs when the rate of evaporation equals the rate of condensation. So what that means is, here in this room, water is it's in the air, so it's constantly vaporizing and it's constantly condensing. But it's happening at the same time, so we don't notice a change. There's no actual change in the humidity, but the processes are still occurring. We don't see them, but they are still there. That's what the dynamic means. Just because we're not seeing a change doesn't mean it's not still happening. With me so far? Good. Okay. All right, so we're going to talk about vapor pressure. Guess what? It's a pressure. It's a pressure. Of a gas. So if we're going to talk about vapor pressure, we have to be vaporized. So it's a gas that's going to be in dynamic equilibrium with its requisite liquid. I just used the example of water. Okay, so vapor pressure depends on the temperature. What tends to happen in Kentucky when it gets hot in the summer? It gets really humid. That doesn't happen in Arizona, but let's think about hot and humid. Tends to be cool and dry. Weather is a little bit of a different phenomenon, but you get the point. It was just an illustration. Okay, so Vapor pressure is temperature dependent. As temperature increases, the vapor pressure increases. Why do we care about this? We care about this because this is how they figure out what is the boiling point. A boiling point is actually technically, chemically, and physically meaning physics, defined as the temperature at which the vapor pressure equals the atmospheric pressure. So as something gets hotter, its pressure rises. Once it's equal with the atmosphere, boom, it's boiling. Does that make sense so far? Okay. Don't let this scare you. It's not as complicated as it looks. You're going to see several of these things. It's just a line. It's a line. Y'all are in calculus. This is algebra 1, okay? It's the equation of a line. This is called the Clapeyron? Yeah, maybe. I don't know. I'm not good at pronouncing names. You've seen what my last name is. Okay. It didn't make it on my Blackboard handout? I didn't get it? Okay. I'll fix it. I'll upload the new one. Thanks for letting me know. All right. It describes a linear relationship between natural log of pressure and inverse temperature. Convenient way to determine heat of vaporization because we care about the slope of the line. When you plot natural log of vapor pressure, that's your Y value, versus 1 over temperature, that's going to be your X coordinate. This whole thing, that's the slope.
Is R the constant that we use from?
Like 0.082.
No, it's going to be the other R, the one with joules in it.
It's like 2.
The 8.3. The one, I'll give it to you. I'll give it to you. So,
Well,
in fact,
H acts as like the X as it like changes. Is it the variable itself?
No, the variables. What you're going to be plotting are temperature and pressure in these forms. Okay.
Yeah.
And then you're going to get a slope, and to find heat of vaporization, you're going to take the negative and you're going to multiply it by, this is our ideal gas constant. So R, again, I will always give you R. Don't panic. R equals, in this case, 8.314 joules per mole Kelvin. All right, so if it's in joules per mole Kelvin, what does that tell us our temperature has to be in? Kelvin. That's the key point here. Make sure your temperature's in Kelvin. That's where you're most likely to mess up. I hope you don't. I'm just telling you what to be cautious for. Because remember, I've done this. I have made just about every mistake possible. I want to prevent you from making the same mistakes. Just know that if you make one, I have done the same thing. And it is okay. Now, what we can do is, if we have 2 points, we're just going to make this a point slope equation. Yeah. So if you have 2 pressures and 2 temperatures, P2, P1, don't memorize this equation. It will be given to you. Okay. I will definitely give you that equation. Okay. So let's talk about the critical point. Critical point. A critical point is the temperature and pressure where our liquid and our gas have the same density. And they're indistinguishable. You can't tell the difference between what's liquid and what's gas. It sort of looks cloudy. There's a nice picture of it in the book. All right, so let's try this out. Okay. Because don't you want to watch me work on these problems before you have to? We're actually going to work a few of them. Okay. This is probably going to be the last thing we get to. If you get lost, let me know. Okay? Don't suffer in silence. Okay, methanol. Now, we're doing this for the same gas. So if I tell you one's methanol and one is butane, you say, no can do. I'm not going to do that, but just in case. You got to be dealing with the same liquid, gas, whatever. Its normal boiling point is 64.6 Celsius. Normal heat of vaporization at the boiling point, 35.2. What is it when we change the temperature to 12? All right. What is the first thing we need to do? Kelvins. Yes. Convert them to kelvins. All right. 64.6. What did I do? Yes. 330. I was looking at the wrong one. 337.6 kelvins and 285 kelvins. Celsius to Kelvin. Add 273. If you want to get technical, 273.15, but I don't like those decimals. You can always be more precise than I am. That's okay. Part of me is lazy. All right, so now let's write the equation that we're going to use. Then we start plugging in, chugging. All right, so natural log P2, P1 equals negative delta H vaporization over R 1 over T2, 1 over T1. This is just algebra. Who thinks calculus is easy and algebra is hard? You're not alone. If you think that. At some point, yeah, especially in Calc 1. All right, so now, key things here. Make sure you don't get P2 and P1, T2 and T1 confused. So, label them in your problem. You don't have to do that. It's a suggestion. I do because guess what? I make stupid errors. So, we're starting out at what pressure?
35.2.
Oh, we don't really know. We're trying to find our vapor pressure. All right. So if it doesn't say it, assume it is the atmosphere. So P1, and for these problems you want to use millimeters of mercury. Who remembers pressure? 760 millimeters of mercury. Okay? P2 is what we're solving for. All right? Which one is T1? Yeah, the 337. This is going to be T1. This is T2. Okay, so let's start plugging things in. So your equation should look like natural log P2, because we don't know what that is, over 760 millimeters of mercury equals negative, what's our heat of vaporization?
35.2.
Yes, 35.2. All right. However, when we talk about R's in joules, this is in kilojoules. We need to make it joules. I'm going to make it joules. I know there's lots of ways you can mess up. So what you can do is you can go to joules, or you can just put 35.2 times 1,000 joules and put it in your calculator later. Just don't forget that. So it's joules per mole. Don't forget the negative sign. Again, I'm going to give you this equation. You just have to figure out what goes where and plug and chug. All right. Now, R, 8.314 joules per mole Kelvin. All right, let's cross some things off. Joules per mole, go away. I've got this way turned crazy. Okay, now let's put our temperatures. I just got lazy and didn't move the decimal yet. All right, so here's how you remember Kelvin. If you forgot to convert to Kelvin at first, now here's where you remember. So 1 over T2, which one is T2? 285. Minus T1, which is 337.6. Parentheses. Now that we have plugged and chugged. All right. The first thing that I did was subtract these.
Did you put your answer in scientific notation?
No. No. All right, let's just work on this right side of the equation first. I think I heard the answer. Who got one? Don't solve for P2 yet. Just solve for this right side of the equation. You're just going to get a number, and it's going to be unitless. Ethan, what'd you get? 2.29. That'll work. The way I did it when I ran, I got negative 2.31. Close enough. It's fine. So, all right. So that means we know that I'm just going to come over here. Natural log of P2 over 760 millimeters of mercury oh, this Kelvin goes up here because joules per mole Kelvin. Anyway, it works out. They cancel. Yeah, did you get 2.29? That works, 2.29. Do you get 2.31? Use 2.31. That's fine, whichever one you use. 2.31, 2.32. I got 2.31. It just depends on how we round. All of them are acceptable. We're going to get just about the same answer. Yes, it is negative. It is negative. You know that because this is going to give you a negative answer. No, that gives you a positive answer. This is the negative. Yeah, so it's negative. All right, what should we do next? The next thing we got to do is we have to get rid of the natural log. Ah, yes. You just came from Kate's class. How do you get rid of a natural log? E to the power. Okay, so we know that E, here, I'll keep my sides of the equation right. P2 over 760 millimeters of mercury equals E to the negative 2.2931. Whatever your value is, it's fine. And then you can get an answer for that if you want to and write it down. Or you can carry this down a line and say P2 equals E to the negative 2.29 or whatever your answer was times 760 millimeters of mercury. They are not pretty problems. But the good news is, by the time you get to physics next semester, you'll just be so used to working hard problems.
Oh, I don't have physics.
Oh.
That's the chemicals.
You don't have physics labs. I thought you still had to take physics.
Yeah, you do.
Do we?
Yes.
Oh, okay.
1 and 2.
That's
I don't
it.
think it's do humans have to take?
They don't take physics labs.
No, we just take the chemistry labs.
All right.
I got 75.4.
There you go. Bingo. 75.4 millimeters of mercury. Now, let's think about this and let's do a reasonableness check. Okay. If we went down in temperature, our pressure decreases. So our pressure should be less than 760. Right on. So all of that to get 75.4. Isn't that fun? No. I know. I understand. I understand. Hey, guess what? Let's do another one. This is the last one we're going to do. Last one we're going to do today. All right.
Do you have an interval for a setup?
Yes.
Can we use the other equation?
The other, what do you mean the other equation?
The y equals
Um,
I like that better. Wait. No, because we have 2 temperatures.
you only have 2 points.
Yeah.
If I gave you a graph,
Yeah.
which I'm probably not going to do, this tends to be how we're going to do these calculations. It's just like calculating complex slope.
Most of it all will be in point slope form then.
Unfortunately. Okay, so let's convert to kelvins first. So let's add 273. This is a negative. Yeah, 231 kelvins. And 298. All right. If you want to, you can go ahead and say this is, multiply that by 1,000 and get to joules. Or you can wait and do it when you plug in the equation. All right. Is our initial pressure given? No. So what do we assume?
760.
We assume it's the atmosphere. So P1 is going to be 760 millimeters of mercury. All right. Plug it in, and then we can chug away. So if you want to rewrite your equation, you can. Or you can start plugging in. Natural log P2, we don't know, P1 760 equals negative heat of vaporization 19.04. I'm just going to say times 1,000 joules per mole over R 8.314 joules per mole Kelvin, which really means this Kelvin's up here in the top. One over, which one is T2? 298. So this one's T2, that one's T1. Minus 1 over, I know I'm slow to write. Y'all go ahead and calculate ahead of me. I'm A-okay. Do all this madness and get a number. Subtract your fractions first, then multiply, then divide. Don't forget your negative sign. Who's brave enough to give me an answer?
7,067?
That is the final answer. Yes, but we're not there yet. I'm not there yet. I'm still waiting to know what this whole side of the equation is.
2.23.
2.23. Yes. Remember, I'm slow. It's okay to work ahead of me. There's no penalty for working ahead. Not on homework, not on anything, not on reading quizzes. I won't give you the test ahead of time, but all right. So get rid of the natural log. P2 over 760 equals E 2.23 P2 E the 2.23 times 760 millimeters of mercury. Yeah, I just said 7,060. I didn't want to write a bunch of decimals. Put a box around it. So, is this pressure really high?
Yes.
Yeah. So, how is propane at room temperature? What states is it in? It's a gas. Yeah. Because it's what we use in our Bunsen burners. So, yes, it should be a gas. It is a gas. Yes, Noah? No, not this time. Okay, so when you do your fraction, this time your subtraction is going to be positive. Okay? Or your fraction is going to be, here your fraction is going to be negative, so then we have the negative times the negative, you're going to get the positive.